Thanks, Gabriela, for the introduction.
My work is devoted to looking for physics beyond the Standard Model, extensions of the Standard Model. The Standard Model was the theory of the electroweak and strong interactions built during the second half of the 20th century. This theory is able to explain correctly all the experimental data we have up to today. But there remain several open questions in the Standard Model. For instance, we know from observations in cosmology that the universe has a large component of dark matter. And in the Standard Model, this dark matter is not present. There is no candidate for dark matter. We know also that we have an asymmetry between the baryons and antibaryons, matter and antimatter. And we need some mechanism to generate it from equal initial conditions. That would be baryogenesis. Also, we know that different areas in the universe must be causally connected. We need some mechanism of inflation at the beginning of the universe. More in the particle physics part, we have the Standard Model, but it has still three very different couplings that have very that are difficult to understand why they are so different. We have the strong coupling, which is large, and two small couplings, the electroweak and the weak coupling. Another problem is the hierarchy problem. The mass of the gauge bosons, of the Higgs bosons, of the scalars, is in particular very sensitive to higher scales in the theory. And we do need some higher scales if we want at some point to incorporate gravity in the theory. And that's also a problem of the Standard Model. And finally, we have another problem, which is the flavor problem. The Standard Model would be perfect if, would be very simple if it was composed only by one matter generation. But we have three copies of the matter fields, which have very different couplings and very different masses. So these open questions have to be answered somehow. We could be, for instance, these first 3 points need some extra components in the model to be able to explain them. But these other three questions are more theoretical questions. In principle, the Standard Model works perfectly well if we just write a theory with three different gauge couplings, rather different, and for instance with three copies of the particles with very different masses and mixings, with different couplings. But really it's not very comfortable. We don't feel good with that. We have too many parameters in the Standard Model and we would like to understand them. Some extension of the Standard Model may explain why we have these features in the Standard Model. That is why I study physics beyond the Standard Model. Among the physics I study, the first one would be grand unification and supersymmetry. As I was saying before, we have three different couplings that here I am representing by alpha, which is the inverse of the coupling square, if you want, of the electroweak or U1 coupling, SU2 coupling, and SU3 coupling. This one is large, is very strong at the electroweak scale, which would be these scales, while the others are smaller. But curiously enough, when we run the couplings, we let them evolve in energy, they meet at some higher scale, or nearly meet in the Standard Model. That was the idea of grand unification scales. At some higher scale, we have only one coupling that would be of order of this size and would explain all the three different interactions in the Standard Model. Also, the matter components in the Standard Model, we have very different fermions in the Standard Model, very different particles. But in in SU5, which is the simplest grand unified model, they are very much simplified. Also, we have 24 gauge bosons, which include the gluons, the strong symmetry gauge couplings, gauge bosons, etc. But we have extra gauge bosons which mediate, for instance, proton decay. Some diagram like this. That would be proton to pi 0. That would be a diagram which would make the proton to decay. So these are very interesting theories because they simplify very much the structure of the standard model. However, with these theories, we still find the problem of hierarchy. And we have now these grand unified theories occur at 10 to the 15 GeVs. And so we have the hierarchy problem. One possibility to solve this hierarchy problem is supersymmetry. In this theory, all the particles in the standard model get a supersymmetric partner that has, in principle, the same mass and the same coupling. And in this way, the mass of the Higgs in the standard model is stabilized. There are other things. For instance, supersymmetry. The lightest supersymmetric particle is stable, and so we have a candidate for dark matter. And we have also improved gauge signification. These are why we think that supersymmetry must be present close to the electroweak scale. In fact, it must be of order of the masses of the supersymmetric particles to solve this problem must be of the order of 1 TeV. So this is one theory that we are looking now at LHC.